Alright, hello folks. In this video we're going to look at the derivatives of trigonometric functions. Get some more rules that we have in our derivative toolbox, so to speak. Oops. Okay, so like I said, it's for a very useful set of functions, especially with applications, the trig functions. One thing we want to keep in mind before we talk derivatives, we want to just remember that whenever we're working with trig functions, the angle measure that we use, it's always in radians. So we're always talking about things being in radians. Okay, so we don't really have a rule so far that we can think of to try to do something a little bit slick with these trig functions. I'm going to start off by looking at cosine, by the way, up here. So when all else fails, we just have to fall back on the definition. Remember the definition. Let me add a derivative of f is given by that expression there, so the limit of that difference quotient. Now the reason I'm starting with cosine is because you may remember with trig functions, and just with trigonometry in general, almost anything you do in trigonometry you can describe in terms of sine and cosine. So if we figure things out for sine and cosine, we're probably in pretty good shape. And I just chose cosine, could have chose sine just as well, but we're going to look at what happens with just one of those examples. So let's look at what we do. Got a fair amount to unpack here. Just looking at this, we've got first of all the formula, f prime for f being cosine. Just plug it into the formula there. This part, using a trig identity, is how we come up with this. That's how we get from there to there. For the next step, what I'm doing is kind of putting together the cosine terms and keeping apart the sine terms. So I broke it up into a difference. Keep the cosine x, cosine h minus cosine x, and then the sine x, sine h in the other term. Now the limit laws that we have for differences, if these individually exist, then their difference exists and we're in business. That's what we're going to use. The last step that we see here from there to there, the limit's looking at what happens as h is changing. So something in terms of x basically is like a constant. There's nothing going on there. So you can pull that sine out. You can pull the cosine out of this term. Because as h changes, it doesn't change. But at that point, we're kind of stuck. Because the difficult part is still here, the limits that remain. We don't have slick formulas for these ahead of time. Now, what I'm going to tell you on the next slide is that we do know what these are. Or we don't know what they are, but we can show them. So if we had more time, we might go through and develop that. I'm just going to tell you that this is true. Maybe you'll believe me. But it takes a little bit of work to figure out. So a direct substitution would give you 0 over 0, so you got to do a little bit more than that. Same thing here, 0 over 0. So there's a little bit of work, but it is something that you can figure out. It's not too bad. But with those in mind, we can go back to our calculation. And again, this was our problem. These were our two problem points there. Well, the previous slide tells us that that is 0, and this is 1. So the derivative is cosine of x times 0 minus sine of x times 1, or just negative sine of x. That is, the derivative of cosine is negative sine. So it wasn't too bad. We started with the definition. We had to remember some trig identities, and we did have to know these limit formulas, which we didn't know ahead of time. One of the things we've been doing a little bit more recently is thinking about graph interpretations of the derivative. And if we look here, the blue curve here is going to be our original function cosine, and the gold is our derivative, which we just showed was negative sine. So you look at the behavior, you look at something like right here over this interval, right along the function, we're decreasing. Well, the derivative over that same interval there is negative. It's below the x-axis. And we've talked about that relationship. Right out here, we get a horizontal tangent line. Slope of a horizontal would be 0, so the derivative would be 0. And you can look at some other points where you get some significant connections along the lines of what we've talked about in the past. So just something to kind of keep in mind, something to think about. Now, the other function we would want to look at would be sine of x. It follows exactly the same pattern. You go through those steps that you did for cosine. A couple little things along the way are a little bit different. In the end, you get, it's the same idea, but some of the specifics are different. But in the end, you find that the derivative of sine is cosine. So we've got it for cosine, we've got it for sine. Those are, like we said, kind of our building blocks for trig ideas. Real quick, looking at the function and its derivative here. So the blue curve is sine, the gold curve is cosine, and you see that behavior where blue is increasing, gold is positive, where blue is decreasing, gold is negative. So with those rules, if we combine those with the quotient rule and keeping in mind a few trig identities, we can find the derivative rules for the remaining 4 trig functions. For example, if we're going to try to find derivative of tangent, we keep in mind that tangent of x can be described in terms of sine and cosine as sine over cosine. So when you're taking, if you want to try and find the derivative of tangent, you can use the quotient rule on this guy. So the derivative of the numerator is cosine times the denominator, cosine times cosine, minus the numerator times the derivative of the denominator, which would be negative sine. Do that arithmetic, you get cosine squared plus sine squared. We know that that is 1 in the Pythagorean property. Looking back, remember with the quotient rule, we take the square of the denominator, so we've got cosine squared. And so we end up with 1 over cosine squared, or just secant squared. So the derivative of tangent is secant squared. Do you proceed likewise for cosecant, secant, cotangent? Everything can be done using what we know about sine and cosine with some trig properties and the quotient rule. And you end up with these 6 results. So derivative of sine is cosine, derivative of cosine is negative sine. Derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. Derivative of cosecant is negative cosecant cotangent, derivative of secant is secant tangent. So you kind of have some relationships that you recognize there maybe a little bit. One thing that's kind of a stumbling block for folks where they get mixed up is whether or not to include those negatives out in front. And one way to remember it is if you've got if it's a co-function, you're going to have that in front. So cosine, cosecant, cotangent, you got that negative. It comes about naturally in terms of the computations, but you just want to remember it. Very easy to get that a little bit mixed up. So for an example, we've got a couple rules that we're going to use here, but we're getting more and more tools in the toolbox, so to speak, so we can do more and more complicated functions, maybe using multiple rules. In this case, we're going to have f prime of x. I'm going to use the sum rule, and then I'm going to break it down into this part and this part, and for each part there, I'm going to use the product rule. So for the first one, take the derivative of the first guy, which is 2x, times the second function, cosine, plus x squared times the derivative of the second, which would be negative sine x. Now plus, looking at the second part up here, derivative of the first would be 1, so I won't write anything, times the second sine x, just sine x, plus the first times the derivative of the second, so x times cosine of x. And I'm going to kind of clean this up a little bit. Going to group like things together. So I've got negative x squared sine x. I've got a 2x cosine and x cosine, so I've got overall 3x cosine. And then a plus sine. And I'll leave it there. That's pretty easy to deal with. All right, last thing to note, we could do some more examples, but I'll leave that to you. The one thing I want to mention though is going back to some limits, some things that we've done in the past. these new limit results that we have with the sine of x over x or the cosine of x minus 1 over x can help us with some additional limit computation. So you can do something like this example here. Now, continuous function, so as long as this is in the domain, we're good, but it's not. So we've got, if we did a direct substitution, we get 0 over 0. It's an indeterminate form, so we're kind of got to come up with something clever. Down the road, we're going to have additional different tools to tackle this a different way, but for now, I want to somehow use this fact. The limit as theta goes to 0 of sine of theta over theta is 1. Now, the variable name doesn't matter. We call this x, theta, t, y, whatever. But what matters is that you've got kind of the single theta there. So you got to have the same thing for the input in the sine function and in the denominator. And that's the problem here. I got a 4x and a 3x. So I got to manipulate that a little bit to get it in a form where I can use this identity. I can't do much with the input of the sine function. You maybe come up with some trig properties and get crazy with that. The denominator is going to be a little bit easier to manipulate. So what I'm going to do is just note the following. So sine of 4x over 3x is the same as 4 over 4 times sine of 4x over 3x, which is pretty crazy, except I can now write this as, and now I'm in business with that part of it, in the sense that the limit as x goes to 0 of sine 4x over 3x is the same as the limit as x goes to 0 of 4/3 times sine of 4x over 4x. Now, this doesn't quite match up because I got the 4x and 4x here, and this is as x goes to 0. Well, all this means is that the ratio here, it's the same, it's the same ratio. I'm just with the 4x there and the x here, I'm basically just going to 0 4 times as fast, but it's the same ratio, if you understand what I mean. So as long as these are the same, this could be x goes to 0 or 12x goes to 0. It doesn't really make a difference because they're both going to 0 at the same, for lack of a better word, let's say rate. So this is 4/3 times 1, which is just 4/3. So it is a little bit specific with some problems that I'll show you somewhere else. We'll do some more complicated ones, but just to kind of prime the pump, so to speak, to kind of get you thinking that hey, we can tackle some new and some interesting limits using these additional identities that we came up with today. So the big idea is the six trig rules, 6 trig function derivative rules, and this is kind of an added benefit. But make sure you commit those to memory. Not too bad, like I said, easy to get the minus, whether you include that or not, easy to get that a little bit mixed up, but with a little bit of practice, you'll have this down solid.